Hi guys, today I want to talk about equilibrium of forces. Equilibrium of forces. For forces to be in equilibrium, the sum of the forces acting on the object is zero. There is no resultant force. There is no net torque or no moment on the object either. No resultant force. The vector addition triangle will return back to its initial starting point when there is no resultant force. So we've got a force body diagram on the left, and then if I just add up the vectors, you can see we end up right back where we started with, and that means that there's no resultant force. So free body diagram shows the forces acting on the body on the left, and then the vector addition triangle shows that there is no net force in this case. No resultant moment. Concurrent forces are forces whose line of action intersect at a single point. So the object on the left, the forces are all going through a single point, or the lines of action of the forces are all going through a single point. So this object will not rotate as the forces act at a single point. However, the object on the right, if we just draw where our lines of action are going through, you can actually see that for the three vectors, the three forces, the lines of action do not meet up at a single point, therefore there will be some kind of rotation. So this object will rotate as the forces are not concurrent. Ladder example, solved with concurrent forces in a vector diagram. So a uniform 6-meter ladder of weight 200 newtons leans against a wall at an angle of 60 degrees to the floor. What is the normal force acting against the wall? Okay, so it's 60 degrees, the ladder. Now, it's a uniform ladder, so the center of mass is going to be in the middle, and that's going to have a force of 200 newtons. That's the weight of the ladder. There's going to be a normal force acting on the ladder from the wall, and we don't know the value of that force, but we would like to find it out. And finally, there's going to be another force at the base of the ladder, and that's going to act not on the actual direction of the ladder, slightly up, and that, if you think about it, well, that's kind of opposing the frictional, is part of the frictional force stopping the ladder from moving or from sliding downwards, but also acting against the weight as well. So it's got this kind of diagonal direction. Now the ladder is not moving, so that means that our forces must be concurrent. So if we look at the lines of action, we can see that they all meet up. Okay, like this. Now, if we do this